Alright, cool. So we did transformations, like translations, horizontal and vertically last time. So this time we're gonna go ahead and do some um, reflections and compressions sort of things. So last video I introduced a general form, which is the y equals, well, I'm gonna write it, I guess. Oh, I can't write it. Which is the y equals af of k x minus h plus p. So I introduced this general form. And this video we're kind of going to go ahead and see how it plays out because we're going to finally be able to see the components of this. So, given a graph of f of x, graph negative f of x on the same axis, describe how negative f of x is related to f of x. So, many people think functions have to be, an actual function, whether it's a parabola or it's a straight line or it's a cubic function or whatever. But realistically, no. As long as I have an output that will give me, as long as I have an input that will give me some sort of output. So anything like a line, essentially this is a function. So how does f of x differ from negative, from negative f of x? So what's the difference here? Well, you'll see there's a negative mark. But last video I talked about how a values changes y and k values changes x. So in our case right now, this seems directly like, hey, look, it's a transformation. So it only changes y. So what does this mean? If we look at this graph right here, we'll see what I mean. We'll see what I mean. So basically, for negative 3, 2, it become negative 3, negative 2. For 0, negative 1, that became 0, 1. And for 4, 1, that became 4, negative 1. So originally, this was x and y. Let's say I gave you a table. So let's say, oh, sorry, that was supposed to be this. So originally we had negative 3, 2, and then we had 0, negative 1, all of that. Now, our new mapping rule. So how do we graph this new function? It's actually x and negative y. So now we have negative 3, and then 2, the negative of that negative 2, and the negative of this is 1, and 0 doesn't change. So now we can go ahead and graph that. So the graph itself, it's actually the same. There is no clear translations yet, simply because we didn't introduce an a value. We only introduced positive and negative. So that's pretty much it. Let's move on to question number 2. So we have a function of 2x plus 1, which is graphed right here. So we want to write an equation for negative x. But notice that this time our f of negative is inside here. Keep in mind, this does not equal to this. These are so different, so drastically different, and you will see why. So when we had, let's say, 2x plus 1, this is our f of x. But when you have a f of negative x, it's actually 2 times negative x plus 1. So essentially that becomes negative 2x plus 1. This is our equation, which is also shown here. So what is going on? What's the big thing? Well, you will know that we are exhibiting a flip, basically. So in this graph, originally it was this way, right? It was going this way because it was positive, and now it's going this way because it was negative. There had to be some sort of reflection here. If you can't notice it, well, you should. So imagine this is an arrow, and we're spinning it 360. So when we spin it across this y-axis, eventually it's going to become this. Oh, that's sticky key. So when you have a negative value here, this is flip about the y-axis. Axis. That's not how you spell axis, but you know what I mean. And later on here, on the left, you might have noticed already, hey look, this is just a flip across the x-axis. So every value, instead of being up here, is now down here. This is like a mirror. This is like an entire mirror that reflects on my point. So up here it becomes down here, right here it becomes here, here, and all of that. So that looks pretty simple. That is pretty simple. Let's move on to the next question. Now we're going to reflect the radical function. So originally we had our function of f of x equal to x minus 2. So this minus 2 is within the radical. So it's a change to x. It's a translation 2 units right. So what exactly do we do now? We're going to go ahead and take y equals negative f of x. Negative f of x. And then we're going to see how these two are actually different. So did I bring I didn't bring the answer. I guess I did not write the answer. Okay, so let's go ahead and write them out, I guess. So first, we're going to see how negative y of x plays out. So I'm going to do this. Why am I not writing? Negative f of x. So remember that your f of x part is actually not changed. So you're not giving in any new input. So essentially, all I'm doing is that I'm just adding a negative sign. So our new output should be negative x minus 2. This doesn't change at all. However, when we have f of negative x, this is going to equal to negative x minus 2. That's some whole different that's some different changes. That's some drastic different changes, in fact. So let's see how that plays out. I don't have a picture, but I'm gonna draw it for you. So originally we had x minus 2. So if you can't tell, that is a horizontal translation 2 units to the right, because it was minus 2 and x is weird. So it would originally look like this, something like this. That would be the square root function. Now, after we flipped it above the the x-axis in part A, this should be our result. It should be something like this. Excuse my horrible line drawing. I'm gonna draw a better one. It's gonna look something like this. It looks like a parabola, but it's in reverse. However, if this was our original function and we flipped it about the y-axis, which is this axis, it should look something like this. I'm trying my best to go a little bit exact here. It should look something like this. We're moving it across the x-axis. And if you have a graphing calculator or you're using decimals, enter it into the decimals. And you will realize, oh look, we are correct. That is how it plays out. And now we're going to go to something more interesting. We're going to understand, oh, this was not supposed to be here. We're going to understand how we're going to reflect a quadratic. So a quadratic is quite different from a square root, simply because when I have a quadratic here, let's say, oh, that's not what I meant to do. If I have a quadratic here, and I flipped it about the x-axis, the y-axis, you wouldn't see anything. Because this part on the right, it will become the left, and the left will become the right. So essentially nothing has changed. So let's see how that actually plays out before I do anything here. If this can get out of the page and stop being so annoying. So let's write the equation first before we do anything. So it should be something like this. If we just add a negative mark directly, it's going to be x squared plus 1. So in our case, we're treating this as a definite value. Like we're defining this value. So for example, just f of x, you can look at it as a variable. So for example, I set y equals f of x. And then I give you negative y. And then y is equal to x squared plus 1. So you will treat this as a bracket, and then you're inputting this as a value in there. Right? So now we're putting this bracket here. So that would actually give us, oh, that's not what I meant to do. So that would give us negative x squared minus 1. Right? So that would be our transformation. So how would that draw out? Let's see if I can draw it out. So originally we had right here. So we were one. Okay, I should probably draw it in a square so it looks better. Okay, now we're actually on the grid. So we were 1 unit above. So we would have something that we would have had something that looked like this essentially. 1 unit above. Draw that. Draw that. So this was our original graph. This is going to be the OG graph. Now when we flipped it, we look, oh, negative x squared. Now this is facing down because we had this value, right? We're going down. We're concave down. So we're looking downwards. But now it's also negative 1. So we're 1 unit's actually below. So now this should look something like this. So that looks like a perfect reflection, even though I drew it not perfectly because I'm such a bad drawer. Could have done better. So I flipped it about the x-axis, and that looks perfect. And now let's see how negative f of negative x plays out. So we're going to change an x into a negative, and everywhere we see an x, essentially. So let's go ahead and try that. So this is going to be negative x squared plus 1. Right? So take a moment to look at it and think, what is this? What is this? If I have this negative mark and I squared it, doesn't that just become a so? Doesn't that just become a positive? So exactly. You have a negative 1 and then x squared, you just become a positive. So essentially, right now, your f of negative x is actually equal to f of x, surprisingly. So just like I proved earlier, there's absolutely no transformation when there's absolutely no flip because you can't flip anything right now. When you flip it across the y axis, you're flipping the right to the left, you're making the left to the right. Now, because the left and the right are the complete same, we can't do anything. So that is the answer to this question. Now we're going to go reflecting another quadratic function, but this time it's a little different now. So let's go ahead and write out the equation first. Y equals negative. You know what? I'm just going to directly expand it. I don't think we have any issues. A, and then B. Okay. So for those that's using decimals, you would probably want to draw it out. For those not using decimals, depends on what you want. So remember, one of the key features that we had on the last example is that we were on the y-axis, so we were right here. So because we were right there, the amount that we have on the left equals to the amount on the right. So that's why there was no flipping that we can do. However, this is not the case because we actually have a horizontal translation here. If you factor out the x, you would notice it. So you could absolutely factor out the x and be like, oh look, our zeros are x equal to 0 and 6, right? So that is some practical math right there. So I don't even need to talk too much about this. So I'm just gonna graph you the original function, which was x squared plus 6x. So our what is it? 2x is negative 6, x equal negative 3. So at negative 3, that's our vertex. And that is negative 9, I believe. So our original graph, it actually looks something like this. Okay, that looks horrible. I'm gonna just draw it better. So this was our original graph. And this is going to be part A. So it's going to have the same it's going to have a vertex but flipped up. So this is part A. And now part B, since we're not on the y-axis anymore, we can actually flip it. So if we flip this there should be it should look something like this. Okay, you know what? I'm going to express. Yeah. So it should look something like this, right? So that's a perfect flip across the y-axis. Now, it also asks for something called an invariant point. So what exactly is an invariant point? So this would play out so much better in decimals, which I'm gonna do it right now, and I'm gonna see if I could take a screenshot of it and then give it to you. But the invariance point is where even after I do some sort of crazy transformation, there's literally no changes. So let's say our original function, it was x squared plus 6x. And then now our new functions is y equal to x squared minus 6x. And then, okay, I'm going to take a screenshot of this so I could put it in there. So right here, this is actually what I have. This is what I just graphed on Desmos. So you will see there's a point of intersection where they actually cross each other. And that point in our graph right now is 0, 0. Right now it's 0, 0. And so that is our invariant point. Because originally, on the original graph, if I was this point at 0, 0, even after I flip it, I didn't move at all, and I'm still this one point. So basically, the point of intersection of the graphs, it's the invariant point. Okay, let me go ahead and erase all of this. Now, that is pretty much the whole class. You can go ahead and practice on some homework on your own if you want, but I'm actually gonna go through some homework today because there's some questions that's a little confusing, some is a little interesting. So let's start. So we're gonna see what happened basically to these graphs. So in one, it flipped about the y-axis. So we all know what that means. When it flips across the y-axis, it's an x transformation. Though, so it was f of negative x, right? Right. So you can go ahead and solve for the equation. I just want to tell you guys and identify the, well, I'm gonna identify the transformation for you guys. And then for b, that's another flip across the y-axis. So it's y equals negative f of x. And then let's see, c, it's the same thing. We're flipping across the y. Now we're also flipping across the y for d. And that's for 4, you can go ahead and graph that on Desmos, and then you will find the reflection. They ask you for both x and y axis, so just always remember, if you want to flip across the x axis, flip, flip of x. When you want to flip across the horizontal axis, that's always going to become negative f of x. When you want to flip otherwise, you're going to have f of negative x. So this is for flipping across the y, and that's for flipping across the x. Should be pretty simple. On the right, I'm going to just give you some quick ideas. So basically, always use Desmos to graph them. And then look at the points if they're invariance point. And then stating the domain, usually it's very easy, especially you have a linear. It's y equals all real number, x equals all real numbers. These are pretty simple. Yep. And pretty much that's it. So if you have any questions, please email me or however you want, reach out to me. I will try to help you to my own best. And then as well, I want you guys to get more practices about the domain and ranges because we're going to move on to actual more harder functions, and I need you to personally be able to quick identify what's going on and see the domain and range. Next class, we're going to learn all about inverse functions.